proceed this time with group 3, maybe one of the most complicated senior designs up to now. Group 3, whenever you guys are ready.
All right.
Feel free to.
All right, welcome, good morning. Thank you for being here. I sincerely appreciate your time. On behalf of Group 3, I'd like to welcome you to our senior design presentation. I want to introduce our group, but first I want to thank you all who helped us get to this point. 4, 5, 6, some of us maybe 7 years that it took to get to this point. It's really exciting. I want to introduce our group. This is Daniel Tran, Javnel Salgado, Dario Lopez, Daniel Mago, and again, I'm Corey Dietrich, and this is our digital industrial composting analyzer.
There should be a clicker up there somewhere.
So as we know, more than 8 million tons of plastic enters the ocean each year. This affects a lot of animals, plants, and also ecosystems around the world. This also affects human health, and for this reason, we have developed a machine that enables others, companies and facilities to create new sustainability materials that can be tested and it can be done. So what is biodegradable? Biodegradable is the process at which microorganisms break down the molecules of carbon compounds. This process can take a few years and also depending on the material composition.
So for our solution, we built the digital industrial composting analyzer based on our design. Our design standards have to follow ASTM 5338 standards, which the 5338 standards is a standard that tests biodegradability of plastic materials under controlled composting conditions. Or the standard allows us to classify the material as biodegradable, as well as in order for us to be able to collect and analyze data, we need 3 systems. Currently on the market, there is 2 to 3 systems. There is one major system that we know about, a unit composting system done by University of Texas for research applications on their master program.
Thank you, Javnel. So what does the machine do? The machine reads, stores CO2 emissions data for industrial polymers and obtains a rate at which materials decomposes within a controlled environment. How do we achieve this goal? Well, we want to focus on the first primary system that enables us to gather the CO2 from the bioreactors, and then there is 2 assisting other systems that help us achieve this by controlling the environment in which the bioreactors are. So here is a little sketch of how a schematic of how the process works. We have some design software and hardware at which helps control the 3 different systems simultaneously. The carbon release control system enables us to read these CO2 emissions and gather all the information that we need, send it to the hardware, and it's writing. The condensing system maintains the temperature of the water that goes through the condenser that we're going to talk about later. And the thermal system just maintains the temperature of the bioreactors at certain temperature as the standards specifically state. Here is our final layout, as you can see, for the machine. Here we have the cold water that goes through the condensers that we're going to talk about in the next slides. And we have here the chamber that all the bioreactors are, which is isolated from the exterior. And these bioreactors will throw air out, which is going to be guided through different solenoids, as you can see here, towards the sensor that will take and gather the data to transcribe it in the software we designed.
Thank you, Dario. The carbon release control system is the most important part of the machine because it measures carbon dioxide emission, our main purpose. As air is pumped through the system, the air filter removes additional humidity, and the air flow meter regulates air flow rate throughout the system. This air is evenly divided among the 12 bioreactors to accelerate natural decomposition. And on the collection side, as air pumps into the bioreactors, carbon emission and air pumps out through additional tubing into the into the solenoids. As the solenoids turn on when we are doing a sampling, passing through the air pump, through the flow meter, and into the gas sensor. There is an air purge that occurs through the system to remove additional carbon dioxide and to prevent contamination. And this graph there shows a graph of an interval of 7 intervals of carbon dioxide concentration levels. As air is pumped into the systems, we can see that there's a higher spike at bioreactor number 2 and 6, where we put carbonated water. This becomes more evident in the next slide, where we show there is an average of these values. As we show, this machine achieved their desired task of measuring carbon dioxide. In the next graph, it shows that our machine is also capable of performing this task of measuring long-term carbon emission. As time goes on, the bacteria and microorganisms adapt to the environment, and the rate of decomposition becomes more evident. Thus, we can compare an unknown sample to 2 known samples, the positive fast-degrading sample and the slow negative degeneration sample. And thus, we can know the environmental impact of the polymers.
Thank you, Tran. For our one of our secondary systems is a thermal control system. This system is required to be maintained at 60 degrees Celsius. The way we successfully did that is we implemented a heating unit system with an automatic sensor, replaced the heating unit in the middle of the chamber, which constantly distributed our temperature throughout the whole chamber at 60 degrees Celsius. When the sensor determines the sensor turns on when the 60 degrees Celsius is too low, but it turns off when it's constant. Our graph here shows our initial response at approximately 250 minutes. It shows the system being at equilibrium at 60 degrees Celsius with a constant temperature for the heating of the system. At launch stability, you can see for the 1200 minutes that we tested that it was constantly at 60 degrees Celsius temperature throughout the whole time, which this proves that our requirement for the thermal control system was met.
All right, thank you. Now I'm going to talk a little more about the condensing system. Now, in order to have accurate readings of the CO2, we must have a condenser unit for each one of the vessels. The condenser units will help us maintain the humidity of the vessel at 60% or above. Every time the water vapor is trying to escape the vessel and the condenser turns it back into liquid, the liquid will naturally fall back into the vessel, therefore maintaining that cycle to maintain the ideal humidity that we need. Each condenser is fed cold water from this external source you can see over there. This external source, we're going to call the cooling system. The cooling system is designed to maintain the water in there at 30 degrees Celsius continuously. Now, just as we did with the heating system, we did a graph where we show for the cooling system at the initial response, once we get to 250 minutes, you can see we achieve the 30 degrees Celsius that we want for our condensing system. And in this graph, we can see the long-term stability. Once we get to 250 minutes, we can see here in this graph that we've been able to maintain that temperature for an indefinite period of time, therefore achieving steady state. Now also, our machine is controlled by a series of programming, and we use 3 programming. We use Arduino, processing, and Python. Arduino was used for the data acquisition and to control the opening and closing of the valve at certain intervals. Then we used the processing in order to transcribe that data, and then we were able to display it graphically through the use of Python. I also wanted to thank the ECML, since they had a big part to do with the programming part of our project. Now the design evolution.
All right, I wanted to talk with you all for a minute about our design evolution process. How did we get from our initial problem to our end result that you see here? And really where we started is with the question, so not how do we create new materials that are biodegradable, sustainable, that have low impact after their usable life is completed, but how do we assist in the testing of those materials to determine which are going to be good? And that's what we created here. And so from there, we knew we had our ASTM standard that we needed to follow for our guidelines. We also knew we had a pretty good example from the university in Texas that a master's student created. We looked at his design, which by the way costs $10,000 to create. And we were able to create this for far less. I'll talk about that in a minute. But we started with our air system. That's, like Tran said, is the most important system in the entire process. we knew we had to start with an air pump, we had an air supply, we had to pass it through the bioreactors, out the other end after being in. We had the opportunity to add an air filter, which not only knocks out excess humidity that might be coming in, because again, you want to control that humidity very closely. You don't want slugs of humidity getting in, depending on what your air source is. But also, you don't want outside biological matter coming in. For example, an insect, if that gets sucked through the line and into your bioreactor, you're going to artificially inflate your CO2, and that's going to screw up your research. Another component that we added, we did a lot of front-end calculations. What size pump do we need? What size lines? How are we going to get air moving through all these systems? When really the question, and when we put it all together, we found that we had a lack of significant airflow because of the unknown restrictions passing through solenoids, that kind of thing, where we didn't have schematics of the internals. We found that we had a lot of restrictions of flow through there. Well, the solution actually was quite simple in that we bought a cheap a medical air regulator. You can dial it into exactly whatever you want. So on the front end, you can put it right at 10. So we have a copious amount of air coming in that we don't need to worry about having a good supply of air, and we can regulate it to exactly the flow rate that we need. You can see here in this picture that just kind of aesthetically how we kind of progressed from where we started to the end result. I'm not going to talk much about the heating unit because that was pretty much a success from the beginning. As far as where you saw the graph that we successfully long-term were able to heat the water. But a really good, I think, example of how when we integrated these systems and took them from individual components to working as a whole, how we overcame some challenges is that the condensing units that we calculated that we would need were massive. The one that the other university in Texas used were huge. They're very expensive. They're going to cost over $200, $250 a piece, and we needed 12 of them. It's not feasible for our project. So what we ended up doing is saying, okay, how can we still get the condensation out that we need, but keep our costs down and still have a functional machine? Well, the answer is, well, let's cool the water more. Instead of using room temperature air, let's get our cooling water colder so that we can use smaller condensers. Now, I want to kind of summarize for you real quick our successes, because I think really it is a complicated machine, and I want to highlight the fact that not only do the individual systems within it work, but the unit as a whole works together quite well. Our CO2 concentrations, when expected, spiked in the places that we expected, and we successfully read those concentrations. Our cooling, heating, humidity found an equilibrium over time. Again, our initial responses brought them to a steady state that we wanted, and over time we see that it maintained those temperatures and humidities. And I want to kind of emphasize that I would consider long-term in a research environment 24 hours. You're not going to leave this for 45 days or 60 days, whatever your test period is. You're not going to leave it sitting there unmonitored for that long. So if you can come in daily and check it, make sure you don't have a water leak. Make sure that you didn't short out your coil or something like that. That would be a success. However, we did test it for longer periods, over 3 days, and it still maintained that equilibrium. Briefly, I want to talk about cost analysis. We ran it for 100 units, but really I don't even want to focus on that. I want to emphasize its use as like a one-off piece, used in a research environment. This provides opportunity for collaboration with HEC and HCC. It provides grant opportunities for research because it was built to the ASTM code and design standards. And I think that its use is not really in a public market to sell, it's in this research industry.
Thank you, Corey. So the functionality, we have tested this machine to make sure that it is, follow the standards and it achieves the goals that we previously discussed. We also test for reliability as we speak for long-term testing to make sure the system acquires its constant equilibrium and every component was able to perform during like these very harsh conditions. And we also think that these future applications for this machine are great. It can open new doors for research, for institutions and faculties, for example, engineering and material science. This will allow to create new materials, to expand the research and beneficially impact the world with these new findings and new materials that we can discover. I would like to thank everybody here to be in our presentation and having the time to listen to our machine everything about our machine, and I would like to encourage you all to ask any questions that you have for us. Thank you.
Any questions? Rafi?
Yeah, so my question is, so you showed me the data. Can you go back to the graphs where you had the bar graphs, I think 12 of them? So my question is, did you, when you started the experiment, did you have a baseline? Do you compare with something that you know of? I know you guys gave the example of a positive and a negative sample, but something like, for example, Apple or something like that, did you go with the sample to kind of go baseline off of? Because none of those are labeled as what those are, so I don't know what that means.
That's a good point. So let me answer that last question first. So these two had carbonated water in them. The rest had
Which two?
the 2 and 6, the two highest ones had carbonated water in them. We would expect, what we want to do is hit it with an excess amount of carbon dioxide so we know the sensors are picking something up, right? I mean, this is like immediate.
Just to follow up with that, do you compare that with the regular or standard results for carbonated water?
Neutral sample,
Yeah.
and the rest of
So-
them. It's not just an empty beaker.
So these other beakers are basically empty. The sensors are very sensible for any kind, so if you breathe next to it, it picks up that. So it has isolations due to the fact that the sensor is very, very reactive. But we wanted to make sure that we're picking up those signals, and the way we did that is basically put carbonated water in 2 of the beakers and read data for a couple of I think it was 7 times that we run the whole cycle. So the cycle runs like, it blows air into the thing, into the bioreactor, sorry, and it picks up that reading, then it purges. So to prevent contamination, and it picks up the next sample, and so on. So it takes a very long period of time to test all these samples, but we run it 7 times for intervals of 5 minutes each one. So it prevents contamination, and we can see the spike and where the samples were taken on.
I think also to your point, and a good thing to note for everyone, is that it will pick up the ambient CO2 in the air. So you have that as your baseline CO2. We're not just putting pure oxygen in. It's room air going in, and so you see that you can almost kind of see it right. There's an average across as you move the air in, and then there's the spike on top of that.
Is any one of them here? Is it this air? Like the CO2 air? Is that any of the measured here shown here?
No.
This is air plus
CO2.
CO2 of the, yeah.
And, okay.
Is that the question? Sorry.
Yeah, no, I was also wondering if you just did air only.
Yeah, well, these ones will be
Oh.
only air, yeah.
So-
All the samples have air
already
flowing
did,
through them,
okay.
yes.
Yes.
And what's the ppm average of it?
Yeah, air is by
ppm is
itself.
about 400 to 500 ppm on the average of air only. But as if we carbonated water, it rises to over 700 to 800 approximately.
So again, all that's showing is our sensors are our valves are being controlled correctly through the Arduino and programming. They're opening at specified intervals. They're sampling consistently without someone being there. And the sensors are detecting excess CO2, meaning if we didn't see those rise in those two, we would think, okay, we know there's excess CO2 in those containers. Why isn't it picking it up? But this is showing that it does.
I think one of the things that you need to consider in your design is the limit of detection of your detector, right? So that just because you can't see it in the bar, it doesn't mean that it's not there, right? So it's something that you really need to think about when you're doing this, because I can tell you, if you put polystyrene in there, you probably won't see anything for a really long time, right?
Yes.
So the next question that I had is, where were the 2 control test polymers or whatever was it that you used that was the positive fast degrading versus the negative one that you mentioned before?
Well, so I want to separate out so we kind of fall into this trap too, where we're not designing an experiment. We're designing a machine that enables experimentation to occur.
Mm-hmm.
So to that end, we wanted to make sure that our equipment is working.
Sure.
I give you that, especially polystyrene and stuff like that, they're going to have very low carbon emissions.
Sure.
It is highly possible that even though those were somewhat expensive sensors, that they were not detecting low enough. I mean, you can get as expensive as you want with gas sampling, right?
Mm-hmm.
So this would be depending on what material you're testing.
Sure, but my point, what I'm getting at, is that you're designing the machine that's gonna do the testing,
Yes.
right?
Yes.
And I, as a chemist, I'm the one who analyzes the data,
Right.
right? So when I go and use a machine like yours, I need to make sure that I know what the limit of detection is,
yes.
because that's gonna help me understand what's going on with the experiment, right?
What is our lower limit of
So,
detection?
well, the limit of how much you can read, it depends mostly on the sensor itself. So, depending on the sensor capability is what you want to like use depending your testing. So, we designed the machine where it easily can be replaced the sensor. You can put a CO2 sensor, you can put a methane sensor, you can put alcohols, nitrogens. So, it depends basically on the sensor that you equip the machine with. Our sensor is between a budget that is, is able to
I understand.
Does it
test.
go down to 10
Yeah.
ppm, right?
No, the ppm that we can read is between like 300 and goes up to 10,000 ppm. So we have a very big range where we can test for the composition. Now these tests will take at least 45 days. That's the standard requirement for them. But if you really want to like trace it, like the graph that, I don't know what it is in the show, but the graph that we showed previously, it will show you that it's almost going to 140 days to actually get the whole curve of it, yes.
Can you show that plot of the 12 samples in the CO2 bars?
Yes.
Okay, so if I'm understanding this correctly, that is not the CO2 concentration above the atmospheric level. That's the CO2 concentration, just raw CO2 concentration coming out of that thing, right?
Yes.
And so you're not feeding it pure oxygen, you're feeding
No.
it atmosphere. And
So
then,
we're pumping in the machine like dry air,
okay,
and this dry air goes through the bioreactors, which in this case were empty.
okay.
So you're picking basically air here,
Except for
except for
2
two
and 6.
that we're adding with CO2,
Okay, what's
carbonated
going on?
water.
What's going on in 5?
5. So therefore, because the sensors we have, they're very sensitive, but at the same time they're hard to calibrate.
Okay.
So it's mostly noise
'Cause-
that we're getting the fluctuation.
The
But that can be fixed with higher quality sensors where they were like sorry.
Okay, the issue I'm having when I look at this, I don't know anything about compost analyzing. But one thing I do know is that, I read it here and there, you hear numbers, usually in the discussion of global warming or something. I know off the top of my head that approximately atmospheric CO2 concentrations are around 400-ish parts per million. So your graph there shows that you're measuring CO2 concentrations below ambient.
Yes.
And if you're pulling in, stuff from the air, that is immediate red flag to me. If you're
So let me
you're-
explain you why that might happen. And the reason for that, what could probably happen is because there could be clots in there, and forming into the hoses, or obstruction of the air flowing through it. So what happens is that's why we have 12 samples, so we can make an average of all of them. What we're really looking into it is the average, which it's actually when we did the average of all of them, it shows out the average at which the air is.
Because if there's a
parts per million.
clog, that's not going to change.
Just we're
the
using
code.
carbonated water. Normally, when we're using this compost machine, we actually use air and carbon dioxide. So when we use a carbonated water, there is a slight clogging that occurs as the water does pass through the tube. But actual testing-wise, this shouldn't occur.
How can a clog change concentration?
Well, no, so I think
It prevents the flow,
The
basically.
flow meter.
yeah. So I think there's 2 parts to that answer. The additional samples. So you don't just have 1 neutral sample. You have 4, right? If there was to be an air, if I walked in as a researcher and saw that was low, wonder what's going on with that one. Maybe I do have an obstruction somewhere that's throwing it off. Maybe my air supply is somehow bad to that. Maybe there's a leak in it somehow. I'm not sure. It would raise a red flag. But that's why you're consistently monitoring your data and say, hey, maybe I need to fix that one. Or maybe you have a bad sensor.
So are the sensors actually measuring concentration? Because I'm trying to visualize how does it clog? Sure, you have lower airflow, but
Yeah,
still
maybe
the
it's
same
not a clog.
concentration.
It might not be a clog. Maybe there's.
Turn around and show no, one of the things, and this is just for clarification, so turn around and show me how. One of the things is that in reality they are artificially trying to have more CO2. One of the things was with carbonated water. But at the same time the project was to have a certain amount of humidity that was way below just the water. So whenever the thing was running, they couldn't condensate
There is,
the amount of
since
humidity.
it's pure water,
And there is a lot of water coming into these
Yeah.
portions like here.
So
it
water is
gets-
contaminating the sensors?
no, let me explain again. So when we test this test has water, carbonated water on the flask, correct? So when you heat up that at 60 Celsius, it oversaturates the humidity of it, right? So sometimes when we run the experiment, it generates humidity. So it floods the pass through the air sometimes, but that's only because that's the way we were testing it.
So the water vapor displaces some of the CO2 in the atmosphere, is what you're saying? Basically.
No. What I'm saying is like the flow gets restricted, so the sensor pick up this change in flow as an anomaly.
Yeah, I think we're gonna walk back on the statement that a clog causes excess or
Okay.
decreased CO2.
Yeah.
That's not correct.
And it's because the sensor is very sensible to the flow of air.
Could excess humidity in the sensor throw off the sensor?
That's
Yes.
why we have like many samples, so you can discard the data that doesn't fit, you know, the correct.
Okay.
That's how you do it. Like when you test data, that you eliminate the data that is off because there's obviously something wrong. So you can linearize the whole process.
I think Tony, that makes a good point. I agree, because this is measuring concentration, so it's not about flow. So
Yeah.
the point that you have water in the line, like you're saying, the water vaporizer shows there's only concentrated changes. And as you mentioned, like one thing I didn't realize that you're doing one sequential test. So that means whatever is in the line, using the same line to do multiple different samples, correct? And
No,
then-
each sample has a line.
Yeah, it's
dedicated to independent
Yeah,
line.
that's why you see the 12 lines here,
Okay.
because each one. And then
But
let
they
me
connect
explain.
though, they merge and back connect to the sensor.
They merge to
And that's what I'm
they
saying,
merge to there.
some of that could be, like you said, some of that, you could have some kind of clogging, but
That is
could be
true,
water
and-
vapor.
But let me
deposition on
explain
that.
you why the
Hold on.
sensor is sensible
Yeah.
to these flows. It is easily sensible to these air flows because the sensor consists in a resistance. So when the air goes through this resistance, it changes the temperature of the resistance. The resistance has to maintain a certain temperature. So if you slowly take out some air, the resistance temperature will change, therefore marking a different value that it's supposed to. So it is very sensible to the flow. That's why we have a flow meter that controls a constant flow to the sensor to maintain this flow constant.
Additionally, in between each sample, there's a purge. So it doesn't have residual, theoretically, doesn't have residual from the previous one. Unless something went very wrong, you slugged a big chunk of CO2 up through there, which you would see, which we have seen, but it does purge. If it's not sampling, it's purging.
Well, for this, I would actually recommend, instead of showing raw data, I think it's good you have raw data, but the way you present it, it added more questions than answers. So you want
I
to
agree.
present this in a way it's easy to consume, probably even have an error analysis for the air concentration, and also show the carbonated water, because we had no idea what this meant. At least personally, I couldn't follow it. The other thing was mentioned was the thermal control. So how do you guys approach it? Like, do you guys use PID tuner? Like, what kind of tools or what kind of?
As far as the heating system?
For the heating and cooling.
So for
Controls
the
for
heating
that.
side of things, it's an automatic dial, so when it's got its own built-in sensor, when it drops below, let's say 2 degrees Celsius below your set point, it automatically kicks
So it's
on
on-off
and
control.
kicks off.
Yeah.
Which I
It's
think is
automatic.
a very good, for the end user, I think it's very good. It's so insulated in there that it kicks on very rarely. That's good. It's not pulling a lot of power while you're not here, kicking on a lot, that kind of thing, just safety. I think it's a good thing.
Okay.
The condensing side of things, I let Dario talk about the condensing side because it's a lot more complicated and it relies on actually several methods to cool.
So the way we design this this cooling system here in order to the condensing to work very well, we use healthy airs and we use cross-flow heat exchangers. These allow us to drop the temperature. And you see that it's 30 Celsius, that's a little bit above the temperature of the ambient. The reason for that is because the pumps that are inside here that are flowing the water through it, they release heat. Also, when the water comes back, the water flows through all the condensers here and comes back. And this insulated chamber goes to up to 60 Celsius. That's where we're supposed to, or maybe a little bit 62 or so. So when the water comes back, it comes back warmer than when it started, right? So this cooling system works in a 60-watt healthy air, which allows it to take out the heat. And also, we use the air temperature to cross flow with the water to release also heat outside of the system to maintain it at 30. So we can even, like, for further better, performance, we can lower that temperature to even condense better in the system. But we reached the standards that we needed, so that's why we stopped there for that system.
This system constantly runs.
Yes.
It's constantly cooling. It doesn't kick on and off as needed.
It's always running.
It's working hard.
So it's not on-off control. I'm asking, so what kind of control are you using?
No, the system it runs all the time. It doesn't have a control. The only thing it has is a thermocouple to maintain, let's say, to tell the person what temperature is it. So you can monitor it visually.
Oh, so there's no controller, just
but it runs very stable at 30 Celsius, as we show you in the graphs. Yes.
And I would definitely invite you to come up and look inside. That's probably the most impressive part with the condensers and the bioreactors and everything. Whenever we're done.
Any other questions you guys might have?
I have one question regarding the software. You said it was programmed with Python?
Yes, Python is used to display the data.
Okay.
Mostly it runs with Arduino and a side program called Processing, which is based Arduino as well. And as Daniel explained, the program, basically Arduino is the one that controls the solenoids. These are the solenoid controls right here. And each of them are connected to these solenoids. And Arduino sends the signal for the cycles to open and close depending on which sample we're gathering. So we basically developed a program that is sequential. So after it completes one, then opens the other one, and so on. The Python, it was only here as
For the user interface?
So Python, what it does is like literally just grab that data that is transcribed in a CSV file and pretty much displays it as a visual, so people can, or the person that is doing the research can look at it and see if there is an anomaly of temperature changes or any other anomaly that it needs to be addressed.
Was that program in-house? Did you program it? Or was
It was developed by us in conjunction with HECML, which is the Untitled organization, the machine learning, and they help us throughout the whole process to program and develop the controls for the machine. Yes, it was a very long process for us to get it running perfectly, but we successfully made it. Yeah. Any other questions?
Thank you again. Good going, Frick.